Welcome to this explainer. Today, we're going to unpack an absolutely incredible breakthrough in how AI is literally learning to write the very code that makes it run. Seriously, if you've ever wondered how these massive, incredibly complex neural networks are actually deployed across different physical computers, well, you're about to see the absolute cutting edge. We're diving into a fascinating new system called KForge, which was developed by the researchers over at Gimlet Labs. And what they've built is essentially an AI that can automatically engineer the highly complex, low-level engine parts for other AI models to run on. It's kind of like a high-performance race car building and upgrading its own engine while it's driving down the track. Okay, real quick, here's our agenda for today. First up, the AI hardware bottleneck. Then we'll meet the KForge agents, look at a cross-platform blueprint, put KForge to the test, and finally wrap up with the future of AI hardware.
All right, let's kick things off with Section 1, the AI hardware bottleneck. Seriously, why can't we just write code once?
So, with modern AI applications, we just aren't doing one simple thing anymore, right? A single agentic AI pipeline might be juggling large language model text generation, some complex reasoning, a bunch of data retrieval, and even external tool use. You might be asking, why can't we just chuck all of that onto one single universal chip and call it a day? Well, here's the catch. Each of those stages has totally different compute, memory, and synchronization profiles. No single accelerator out there is the perfect fit for all of them at the exact same time. For maximum efficiency in a real production environment, you actually need to route different stages to the hardware best suited for it. But doing that, that creates a massive systems design headache.
The reason this is so insanely hard really boils down to something called compute kernels. Think of compute kernels as the custom-built engine parts of an AI model. We're talking the timing belts, the spark plugs, the highly optimized math operations that actually crunch the numbers under the hood. To run an AI model on a brand new chip, you cannot just copy and paste the old code. Porting these kernels isn't a simple language translation. It requires a totally new engine design for every single piece of new hardware, simply because every chip has its own unique memory hierarchies and bandwidth limits. You've got to write in languages like CUDA, Cycle, or Metal, and that requires some incredibly specialized low-level knowledge.
So here is the brutal reality we're facing. In a perfect, ideal world, we all want a write once, run anywhere setup. But the current reality, it's tough. Writing these high-performance compute kernels demands rare, super deep engineering expertise. And as these kernels get more and more complex, relying on human experts to hand-tune code for every single new chip that hits the market, well, it just doesn't scale. We are physically bottlenecked by the number of human experts who can actually write this stuff. What we really truly need is an automated robotic mechanic.
Which brings us to Section 2, meet the KForge agents. Let's talk about automating that AI mechanic.
So how does KForge fix this? Well, it doesn't tackle the bottleneck with just one massive, do-it-all AI. Instead, it uses two collaborating large language model agents, and they act a lot like a student and a teacher. First up, you have the generation agent. Think of this one as the student. It writes the initial code and progressively refines it just to make sure it actually compiles and runs without crashing. Then you have the performance analysis agent. This is our teacher. It doesn't actually write the code. Instead, it carefully reads the profiling data, the raw metrics of how the hardware performed. And then it gives very specific recommendations back to the student on how to make that code faster.
The workflow essentially happens in two continuous loops. First, there's a functional pass. The generation agent proposes a kernel, and the system asks a few basic questions. Does it compile? Does it execute? Is the math even correct? If it fails any of those, the error feeds right back, and the agent tries again. It just relentlessly loops until it gets a working kernel. But once it is correct, the system shifts into the optimization pass. This is where that performance analysis agent steps in, looking at how the hardware is being used and suggesting clever tweaks to close the performance gap. It's this beautiful continuous feedback loop of synthesis, verification, and optimization.
Okay, on to Section 3, a cross-platform blueprint. Let's see how they're breaking the vendor lock-in.
What we've got here is a truly unified, cross-platform framework, and it proves the sheer breadth of what KForge can do. You start with a standard PyTorch reference, which is the high-level code that most AI developers are already using. From there, KForge automatically selects and lowers that code down to the absolute perfect, optimized programming model required for your specific target hardware. It completely abstracts away all that agonizing low-level engineering that usually locks developers into a single hardware ecosystem.
And KForge is definitely not playing favorites here. It can generate code across an incredibly impressive array of hardware targets. We are talking NVIDIA GPUs using CUDA or Triton, AMD GPUs using HIP, Intel Arc using Cycle, and yes, even Apple Silicon using Metal. It supports 4 different accelerator vendors and 6 distinct programming models. This level of flexibility is literally exactly what the industry needs right now to mix and match hardware based on cost and availability instead of being locked into whoever employs the most human kernel engineers.
Which brings us to Section 4, putting KForge to test. It's David versus Goliath and the new frontier.
So, the big question, does an AI mechanic actually write better code than a human expert? Well, the researchers first tested KForge on the absolute top-tier NVIDIA B200 chip against TensorRT LLM. Now, TensorRT LLM is the gold standard. It represents years of hyper-optimized, hand-tuned engineering by NVIDIA's very own experts. It's Goliath. But against this Goliath, KForge, our AI David, achieved a 2.12% end-to-end throughput gain on an AI inference benchmark. Now, you might hear 2% and think, that's kind of small. No way, it is not. In the world of hyper-optimized production runtimes, finding even a fraction of a percent of extra performance is brutally difficult. Achieving over 2% end-to-end improvement against years of dedicated human engineering is a massive validation of this agentic approach. At a data center scale, that 2% compounds into millions of dollars in compute savings.
But wait, it gets even more amazing when you look at emerging hardware. They also tested KForge on the brand new Intel Arc B580 GPU. Here, comparable hand-tuned reference code from human experts didn't even exist yet, so KForge was essentially acting as a rapid bring-up tool. And the result? KForge achieved a massive 5.13 times speedup over the standard PyTorch compiler baseline. When you don't have an army of human engineers who have spent years optimizing for a specific chip, KForge steps right in and bridges that gap almost instantly.
When you dig into the specific execution times, the picture is pretty dramatic. Just think about a drop from 23 milliseconds down to just under 6. How on earth did the AI achieve this? Well, the performance analysis agent guided the generation agent to use incredibly clever, hardware-specific tricks. For instance, it used layer-wise fusion, which collapses multiple operations into a single step so the chip doesn't have to keep writing data back and forth to memory. It also utilized mixed precision execution, meaning it ran the heavy math in a faster, lower precision format while somehow keeping the final results highly accurate. The AI basically figured out exactly how to squeeze every last drop of performance out of the silicon. Let's wrap up with Section 5, Future of AI Hardware, looking beyond the benchmarks.
You know, the researchers really hit the nail on the head in their conclusion. It brilliantly illustrates where this entire industry is heading. This is absolutely not just a theoretical academic exercise anymore. Using collaborating AI agents to write, verify, and optimize compute kernels is ready for real-world production today. It completely solves the human bottleneck. You just no longer need to wait for a tiny pool of highly specialized engineers to manually translate software for every single new piece of hardware that enters the market.
Which leaves us with an absolutely massive question to ponder as we finish up this explainer. Right now, dominance in AI hardware isn't just about who physically manufactures the fastest silicon, it's about who has the most mature, hand-optimized software ecosystem protecting that silicon. It's a huge moat. But if AI agents like KForge can automatically write perfectly optimized code to run AI on absolutely any chip out there, are the days of a single company dominating AI hardware finally over? It's an incredibly thrilling frontier, and it honestly seems like the AI itself might just be the key to unlocking it. Thanks so much for joining me on this deep dive, and definitely keep your eyes peeled on how these agentic systems continue to evolve.